everyone. Today we're talking about square root functions. So dilations of radical functions, a square root function, contains the square root of a variable. Square root functions are a type of radical function. In order for a square root to be a real number, the radicand, which is the value underneath the radical sign, cannot be negative. Values that make the radical negative are not included in the domain. So this is our first graph we've had where the domain is now all real numbers. So a parent function is the simplest form. So the parent function is the square root of x. The graph looks like this, where it's a curve, and our domain has to be greater than or equal to 0. X has to be. And range is also greater than or equal to 0. So now to do number 1, to make our graph, we need to make a table and choose non-negative values for x. So we choose 0, 1, 4, 9, because we can choose anything we want. So I chose perfect squares. So the square root of 0 is 0, times 3 is 0. Square root of 1 is 1, times 3 is 3. Square root of 4 is 2. 2 times 3 is 6. Square root of 9 is 3. Times 3 is 9. So we plot those points. 0, 0, 1, 3, 4, 6, and 9, 9. Which doesn't fit, but it'd be there. 0, 0 is a point. It is not an arrow. At the right end, it is an arrow. It's a point at 0, 0 because I can't have anything negative. So my domain is x such that x is greater than or equal to 0. Or we could write that as 0 in the box to infinity, because 0 is included. Our range is y such that y is greater than or equal to 0. Or again, we could do 0 to infinity, but again, 0 is included. Now, if we wanted to discuss how this is comparatively, we would say that it's dilated because it starts at the same point, has the same trend, but it goes higher. So, graph each function and compare to the parent function. State the domain and range. So this is stretched vertically. So here, again, we make a table. And again, I'm taking the square root of x, so I'm going to choose perfect squares. 0, 1, 4, 9. Square root of 0, 0, times 3 halves is 0. Square root of 1 is 1, times 3 halves is 3 halves. Square root of 4 is 2, times 3 halves is 3. And the square root of 9 is 3, times 3 halves is 9 halves. So we plot that. Again, 0, 0 is a point. Does not get an arrow because that's the smallest it can be. 1 is 3 halves, or 1.5. 4 is 3. And 9 is 9 halves, or 4.5. Starts at 0 and goes. My domain again is x is greater than or equal to 0. My range again is y is greater than or equal to 0. And again, it is stretched. Number 2, it's 4 radical x. So again, I make a table. I'm still taking the square root of x. So I choose numbers that are positive, that are perfect squares. Square root of 0 is 0, times 4 is 0. Square root of 1 is 1, times 4 is 4. Square root of 4 is 2, times 4 is 8. Square root of 9 is 3, times 4 is 12. Plot what we can. So 0, 0, 1, 4, 4, 8, and 9, 12 definitely isn't going to fit. So you can see this is stretched significantly more. It goes up much higher before it starts to curve. Our domain is still y is greater than or equal to 0, and our range is still y is greater than or equal to 0. Because domain is all the x values, range is all our y's. Number 3, I want you to pause and try it for yourselves. So I made my table. 0, 0, 1, 5 halves, 4, 5, 9, 15 halves. Plotted. It's stretched again, meaning I'm pulling it up and I'm making it higher, but it's the same pattern. Domain is still x is greater than or equal to 0. Range is still y is greater than or equal to 0. So, next page. Translations. Oops, I didn't mean to shrink it. Reflections and translations of radical functions. Radical functions, like quadratic functions, can be translated horizontally and vertically, as well as reflected over the x-axis. To draw the graph of y equals a, square root of x minus h plus k, follow these steps. Step 1, draw the graph of y equals a radical x. Graph starts at the origin and passes through the point 1a. If a is greater than 0, the graph is in the first quadrant. If a is less than 0, the graph is reflected across the x-axis. Translate the graph k units up if k is positive and k units down if it's negative. Translate the graph h units left if h is positive and right if h is negative. So let's see how this works. So example, graph negative square root of x plus 1 and compare it to the square root of x. So we start by graphing radical x. So that's 0, 0, 1, 1, 4, 2, and 9, 3. Now this is a horizontal translation 1 unit to the left, because remember it's square root of x minus h. So since it's x plus 1, that's x minus negative 1. So h is negative, so we go left 1 and reflect it over the x-axis. So reflecting over the x-axis brings us down. So when we reflect over the x-axis, we get 0, 0, 1, negative 1, 4, negative 2. You get that pink graph. Then shifting it left 1, 0, 0 becomes negative 1, 0. 1, 1 becomes 0, negative 1. And 4, negative 2 becomes 3, negative 2. And we get that red curve. The domain, our x values now start at negative 1. So our domain is x is greater than or equal to negative 1. And the range is y is less than or equal to 0, because it's below the x-axis. So I want you to pause, and I want you to graph 1, 2, and 3, and come back.